We've already talked a little bit about the idea of basis. We just didn't call it that. Back in, oh gosh, I don't remember what section it was, but we said in R3, well, we could do it in R2 as well, but I'll just go with R3, that we had these three vectors, I, which was 1, 0, 0, J, and K. And what's special about these vectors is that they are each pointing in a nice sort of standard, this one's I, standard direction of the various, in this case, three axes. This is the I vector. It's the vector 1 in the x direction, 0 in the y or z. This one goes 0 in the x direction, 1 in the y direction, and 0 in the z direction. And this one goes 0 in the x and y direction, but 1 in the z direction. And we gave these special names. Collectively, we call these the standard unit vectors. Each one of these is a standard unit vector in a particular direction, okay? In this section of the textbook, we're going to be looking at some of the things that we can do with vectors like this. In this particular case, we have these three vectors. One thing I can observe is this, that since I have three vectors and I'm in R3, there's a very good likelihood that these three vectors will span R3. We had a theorem back in section 4.2 that tells us how to figure out whether a set spans Rm. Here we're talking about R3. So how do we know whether this set of three vectors spans R3? That theorem said that the three statements were equivalent. The span of the set is equal to R, in this case R3. So the span of the set will be equal to R3. The system AX equals B, that system has a solution no matter what B is. I can pick any B and I'll be able to find a vector X that will satisfy this equation, where the vector A is 1, 0, 0, 0, 1, 0, 0, 0, 1. So this equation, x1, x2, x3, equals some vector a1, a2, a3. No matter what a1, a2, and a3 are, this system has an equation. That's one way, well, that's one of the three statements, okay? So this was statement 1. Sorry, this was statement 2. Has a solution. This was statement 2. Statement 1 was a span of the set. I'm just going to call my set S is equal to, in this case, R3. And statement 3 was the reduced echelon form of A has no 0 rows. So reduced echelon form has, let me back up a little bit, of A, where this is A, has no 0 rows. And those three statements were equivalent. So if I know this, I know this. If I know this, I know this. And what I'm going to use here is if I know statement 3 is true, then I know statement 1 is true. They're equivalent, right? So if I know one of them is true, then the other two must also be true. So I'm going to make up a matrix with these vectors. I've already done it once, but I'm going to do it down here again just to make my point. There's vector A. The reduced echelon form of A has no 0 rows. Well, this is the reduced echelon form of A because I'm dealing with the standard unit vectors, right? So there are no 0 rows. Therefore, since this statement is true, the span of S is equal to R3. So this collection of three vectors spans R3. Something else we can say about this collection of vectors is that they are linearly independent. Let me do this. I'll take that collection again, 1, 0, 0, 0, 1, 0, 0, 0, 1. And it turns out, actually I'll use an augmented matrix instead. It turns out that if this matrix, when I row reduce it, it's already row reduced, if that matrix, if the system of equations that produces this matrix only has the trivial solution, in other words, the only solution to this is x1 equals 0, x2 equals 0, x3 equals 0, if that's the case, then these three vectors are linearly independent. Well, there's my vector matrix, right? And there is only one solution. I mean, the vectors are already, the matrix is already in reduced echelon form. So if I read this off, this is x1 equals 0, this is x2 equals 0, this is x3 equals 0. There's nothing else I could do with that. So this must be the only solution. Therefore, we can actually also say that the vectors I, j, and k are linearly independent. Well, those two things together, the fact that the collection of vectors spans the space that we're talking about, the space that we're in, and the collection of vectors, or the vectors in the collection, are linearly independent. Those two things together are what are required for a collection of vectors to be what's called a basis. And so now, in addition to calling these the standard unit vectors, we might call I, j, and k the standard basis vectors. This collection of vectors has these properties. As a collection, they span R3, and it's implied here that they are a minimal spanning set, but that's also the case here, and that they are linearly independent. So now we have a definition for basis. These two properties have to be met. And we've also identified this very special basis. The vectors in this particular collection of vectors, I, j, and k, are called the standard basis vectors. Okay, so now we know what a basis is, and we know how to identify one. But the thing I want to point out now is that while we have found a basis for R3, we found a collection of vectors that spans R3, and that collection of vectors is linearly independent. It's not the only one that could do the job. There are other collections of vectors that span R3 and that are linearly independent. And I've found one for us to play with, so I'm going to do that on the next screen. Okay, this is a collection of three vectors in R3, and I'm going to show you that this collection also forms a basis for R3. The requirements are that these three vectors must be, as a collection, linearly independent, and that they also span R3. We'll do the test for linear independence first, and that is to say, does the matrix, or the system of equations that produces this matrix, have more than the trivial solution? If it has only the trivial solution, then our vectors are linearly independent. If we end up with a zero row, for example, then we know we've got some free variables or free values in here, and there's more than one solution. But if we can come up with a row-reduced form of this that indicates there's only one solution, and that solution is the trivial solution, that x1, x2, and x3 all have to be 0, then we'll know that this collection of vectors is linearly independent. So let's do some row reduction. I'm going to go ahead and do this one by hand because I think it's good practice to continue to see that process so that we know what's actually happening here. I'm going to take -2 times row 1 and add it to row 2 and replace row 2 with the result. So my first row doesn't change. My last row in this step is not going to change. So I just noticed I could scale that last row quite easily. But let's do one thing at a time. I'm going to take -2 times each of these values and add them to each of these values. -2 times 1 is -2. When you add that to 2, you get 0. -2 times 4 is -8, plus 5 is -3. -2 times 0 plus 0, and -2 times 0 plus 0. Now I'm going to scale the second row. I'm going to say -1/3 times row 2 and put that into row 2. And I think while I'm at it, I'll also do 1/3 times row 3 and put that into row 3. That'll just make my next step easier. So in this case, my first row is not going to change. My second row becomes 0, 1, 0, 0, and my third row becomes 1, 2, 1, 0. It's not, remember, strictly speaking, necessary to have this line down the middle here, dotted line. It can be convenient, it can help you see the solution, but it's not strictly speaking necessary, so I may start leaving that off. All right, in my next step, I've got, my second row is in the form I wanted in now, right? But my third row still has a 1 here, so now I'm going to take the opposite of each of these values and add them to these. So that means taking negative row 1 and adding it to row 3 and putting that in the position of row 3. So that's going to give me no change in row 1, no change in row 2, and row 3 is going to be the opposite of 1 plus 1, which is 0, the opposite of 4, negative 4, plus 2 is negative 2, the opposite of 0, plus 1, and the opposite of 0 plus 0. All right, and now if I multiply this number by 2 and add it to this one, I'll get a 0 in that position. So let's do that next. I'm going to take 2 times row 2, add it to row 3, and make that my new row 3. So that does not change row 1, does not change row 2. It changes row 3, 2 times 0 plus 0, 2 times 1 plus negative 2, 2 times 0 plus 1, and 2 times 0 plus 0. And the last thing I have to get rid of here is this 4. So I'm going to take this number, this 1, multiply it by negative 4. So multiply this row by negative 4, add it to this row. That's negative 4 times row 2 plus row 1. That becomes my new row 1. So row 1 is the one that's changing in this case. And that gives me 1, 0, 0, 0. Okay, so as you can see, I have this now in reduced echelon form, and this is my x1 value, my x2, my x3, and they all have to equal 0. So this system, right, the system that brought about this matrix, only has the trivial solution. So now we can say that the collection of vectors V is linearly independent. And that's one of the criteria for being a basis. So we're well on our way to establishing that V is a basis for R3. The other requirement is that the collection of vectors minimally span R3. Well, we had a theorem in the previous section that said that one of the ways to tell whether a set of vectors spanned the space it was in is if there were, in its reduced echelon form, there were no 0 rows. Well, there are no 0 rows here, so we can also say that V spans R3. And these two things together tell us that V is a basis for R3. Well, we already found one basis. It was the standard unit vectors, and we called that collectively, we called that collection of the standard unit vectors, we called that the standard basis. But it's not the only one. Here's another one. This collection of vectors is also a basis for R3. Now that we have that under our belt, there's some other observations that we can make that will really kind of tie all this together. So I'm going to go to the next screen and we'll talk about that next. Here is a collection of vectors. We're calling it S, and the vectors, the individual vectors in this collection, in this set, are in Rn. Now that could be R3 or it could be R17, right? We don't know what that number is, but once we do, or even if we don't, it's fixed for any particular situation we're talking about. So there are three possibilities here. The number of vectors in the set is smaller than the space that you're in. In other words, you have only 2 vectors in your collection, but you're in R3. Right? That's one possibility. Another possibility is that you have more vectors than you do the space that you're in. So for example, if you are still in R3, but you had 4 vectors or 5 vectors, that's a possibility. Another possibility, of course, the only other possibility is that the number of vectors in the collection that you're playing with is actually equal to the dimensions in the space that those vectors are in. So 3 vectors in R3, 7 vectors in R7, 2 vectors in R2, that kind of thing. Those are the only 3 possibilities here in terms of the size of the collection and the dimensions of the space. I don't know if you noticed, but when we were playing around with span, there were always there were always exactly 2 vectors in the span of R2. That collection of 2 vectors is not unique, but there are only ever 2 vectors in the span of R2 in a minimally spanning set, right? If you don't have enough vectors, then you can't span the space. For example, if you only have 2 vectors, but you're in R3, then it's not going to, those 2 vectors don't span the space. They're not big enough, right? They're not collectively big enough to encompass the entirety of R3. So the way we're going to note that is we're going to say that if there aren't enough vectors, then the collection of vectors in that space, in that set, does not span the space. So of our 3 possibilities here, if the number of vectors is fewer than the number in the dimension of the space, then the vectors don't span that space. If K is too big, if you have more vectors in your space, more vectors in your collection than you do dimensions in your space. Say you have 3 vectors, but you're in R2, then one of those vectors must be a linear combination of the other 2, right? So if K is larger than N, if there are more vectors than there are dimensions in your space, then S is not linearly independent, so S is linearly dependent. Okay, so that's what we can tell about a set of vectors, a vector space, if we know that the number of vectors is smaller than the dimension or the number of vectors is larger than the dimension. But what can we say about when the number of vectors in the space is the same as the dimension? If this is not true and this is not true, can we automatically say, oh, then S must span R3 and S must be linearly independent? And the answer is no. But there are 3 things that we can say are equivalent. In other words, just because K is not less than N does not mean it's going to be equal. It could be greater. Just because K is not greater than N doesn't mean that they're going to be equal either. It could be less. So we cannot say if K is equal to N automatically that S spans R3 or Rn. That should be Rn. Sorry, let me fix that real quick. We can't make that assumption, but what we can say is that if we know that S spans Rn, we can also assume that S is linearly independent. And we can say that S is a basis for Rn. And what's so powerful about this is that when we say that the following statements are equivalent, what we're saying is that if I know one of these, I automatically know the others. So if I know S now, if I know S is linearly independent, that all 3 in those vectors in the set are linearly independent of one another, then I also know that the same set, the same collection of vectors spans Rn. And I also know that S is a basis for Rn. Right? We said that the definition of a basis was that the collection spanned the space and the collection was linearly independent. But now what we're saying is that you only need one of these for the basis, for the collection to be a basis, because all 3 of these are equivalent. If I know S spans Rn, then I also know that it's a linearly independent collection, and therefore it is also a basis. So all 3 of these are equivalent to each other. These only occur if K and N are equal, What we don't necessarily know is that if k and n are equal, these must also be true, right? That is not what we're saying here. We're saying that if k and n are equal and we know one of these three, then we know the other two as well. If k and n are equal, we are not necessarily guaranteed any of these. But if we find one, then we know the other two are also true. And this is called the basis theorem. So if you're looking for a basis of R3, for example, the first thing to look for is to see whether you have enough vectors in that space. If you've only got 2 vectors in R3, then you certainly don't have a basis because it doesn't your vectors don't span the space. If you have 4 vectors, but you're in R3, there are 3 components in each vector. If you have too many vectors in the space, then you don't have a span because that particular collection of vectors is linearly dependent. Now you might be able to pull one of those out and use a smaller set, use a subset, right? But if you do that, you're no longer working with this set of vectors. So you have to rename your set. So look to see whether the vectors in your set are too many. If they're too numerous, then you don't have a basis because you don't have linear independence. If you have the same number of vectors as you do dimensions in your space, then you need to test for one of these. And once you've tested for one of these and found one of them to be true, then all 3 of them are true.